In this segment, we're going to look at two very common algorithms for sorting and searching, one of each, and we will practice manipulating arrays and writing code that manipulates arrays using these two common algorithms. This is an important point where you will look at code that's more complex than we've seen up until this point. And it's important that you walk through this code until you're comfortable with exactly what's going on in the bubble sort algorithm and the binary search algorithm. It's very common that you would want to, in your programs, sort some data, and it might be that you want it sorted alphabetically or ascending order or descending order, some sort of numerical order. And there are many known algorithms for achieving this, and this is a fairly complicated problem, so you wouldn't be expected at this point to solve this problem from scratch. You would look at the existing algorithms and understand them. And the sorting algorithm that we're going to look at is called the bubble sort. And first we'll look at it without code. So the objective is that we want to go from an array that is not in sorted order and rearrange the numbers so that they are in sorted order. So there's an array, a very small one of only 6 elements, that is unsorted, and then after processing with this bubble sort algorithm, it's in sorted order, and in this case sorted ascending order. So let's look at the bubble sort algorithm in action before we even begin to think about the code. I drew this arrow to indicate that we're going to sort it going up in ascending order, and we have some numbers in an array that are not sorted. The first thing we're going to do is compare the first two elements in the array, 95 and 75, and we'll say, are they in the right order? And if they're not, then we'll swap them. And these two numbers are not in the right order for an ascending sort, so we're going to swap the 95 and the 75. I redraw the whole array here, but we only have one array. We're sorting these numbers in place, which means we're not making another array and putting the numbers in it. We're using only this one memory location for the array, and we're going to rearrange the numbers. So the first two are now swapped, and then let's look at the next pair of numbers, the 95 and the 87. Are they in the right order? Well, they are not, so we're going to swap them. And now 87 and 95 are swapped. Keep going. Look at the next pair of numbers, 95 and 68. They're not in the right order, so we'll swap them. 95 and 98 are in the right order, so we'll leave those two alone. And look at the last pair. 98 and 88 are in the wrong order, so let's swap those. So now what we've just done is called a pass through the array. We've looked at the pairs of adjacent elements in the array, and we've done one pass. And you might notice that this array is not sorted yet, but it's more sorted than it was. So if we did the same thing again, if we went through looking at the pairs of numbers, then eventually this array would become in sorted order. And what does eventually mean? How many times would we have to do that? We would do it n minus 1 times, where n is the number of elements in the array. In this case we have 6 elements, so we would go through this array 5 times, looking at the adjacent elements and swapping them as necessary. The other thing that you might notice, after one pass through this array, the largest number has bubbled up to the top. This is what's called a bubble sort. Why it's called a bubble sort. Each time through, you're guaranteed that one more number will be in the right place. Some people call this a sinking sort instead of a bubble sort. If you want to think of it as the largest number sinking over to the right, then that's okay too. I think the more common name lately is called a bubble sort. So let's look at a pseudocode solution. for a pass through the array. So for each pair of elements in the array, we're going to check if the pair is out of order, and if it's out of order, then swap that pair. So it's a simple for loop with an if statement, and swapping the two elements of the pair will write that in code. So this is one pass through the array, one for loop, but we also said that the array is not sorted when you do one pass. We have to do this pass over and over. Well, how do we do something over and over? We put it inside of a loop. So let's add another loop outside of this, and we'll say that should actually be size minus 1. We don't have to go size times, which would be 6 in that array. We would go size minus 1 times through the array, and then each time through that outer loop we'll do this inner loop where we compare the elements and do the swapping as necessary. So what I'd like you to do is to walk along with me in the development environment, developing the solution, the C code solution to the bubble sort for sorting a small array, keeping in mind that what we might actually need to be doing is sorting a very, very large array of data. The algorithm will be the same. It's just how many times will these loops go that makes it different, and we'll just work with a small array so we can see exactly what's going on. So let's go into the development environment now and solve this problem. So here we are in the development environment, and I have declared an array of size elements called grade, where size is 6, and I filled in the numbers that we had in the slide. So we have this array of 6 elements, and we're going to sort it using a bubble sort. So I encourage you to pause here and get your development environment project up to this point and develop this algorithm along with me using your own code, and then you'll have a better understanding of it. So to warm up, let's make a loop that outputs these array elements. So I get 0, I is less than size, I++, and we'll just print the array elements so that we can see that they're not in sorted order. So it's grades sub I that we'll output onto the screen, and let's see if just that is working so that we can use the debugger. Well, of course, I forgot something already. Let's declare a variable I to use for the loops, and I should be using the F7 key to compile. I want you to have good habits, and the build has succeeded, so let's run this and just see if we can spit those array elements out onto the console in an unsorted way. A carriage return after it would have helped, but that's okay, there they are. Okay, so we're going to start the bubble sort algorithm, and first we'll make the inner loop, which is make one pass through the array. So we want to compare each of the pairs of elements, 95, 75, 75, 87, and so on. So let's make a for loop. I get 0, I is less than, and we're going to use size minus 1 and go through each one. Why are we using size minus 1 instead of size? Well, we're going to use I as 0, 1, 2, 3, 4. We don't want I to become 5 because there's nothing here to compare. So the last value of I for which this condition is true is going to be 4. 0, 1, 2, 3, 4, and we'll compare 4 and 5 in the last pass. Sorry, I don't want to use the word pass. In the last iteration through the array. So now we're going to compare the two elements and see if they're in the right order, and if they're not, then we're going to swap them. So make it a fill-in-the-blank problem. What are we going to compare to what? Well, we're going to compare grades sub I with grades sub I plus 1. So let's say if grades sub I is less than grades sub I plus 1, then we want to swap them. Is that right? No, I have the relationship backwards. If the one on the left is greater than the one on the right, then we want to swap them. I do that quite a lot. I just write down the relational operator and then see if it makes sense after I've written it down. It's quicker for me, and probably you, than if we just look at it for a long time and try and see what it should be. So now we need to swap grades sub I and grades sub I plus 1. How are we going to do that? Well, we need a temporary variable to hold one of the values. You can't swap two variables without putting one someplace else. It would be like two people trying to switch the chairs they were sitting in without either of them standing up. So let's put into the temporary variable grades sub I, and then in grades sub I put grades sub I plus 1, and then in grades sub I plus 1 we'll put the temporary variable. See if that makes sense to you. On the first iteration, where I is 0, grades sub 0 has 95. Grades sub I plus 1 has 75. 95 is greater than 75. That's true. So take grades sub 0, which is 95, and put it in temp. Then grades sub I, this location, will get grades sub I plus 1, which is this value, so 75 will move to the 0th location. And then in the I plus 1, which is the 1 location, we'll put the temp variable, which holds the value 95. Okay, let's copy this code and output the array, just so that we can see if things are going right. When your indentation gets mixed up like this, I hope you're using the development environment to sort it out for you. You can do a Control-A, Edit, Advanced, Format Selection, and look at that, it cleans up the indentation for you. So I'm going to add another output a carriage return here, just so that it will be neater, and we won't get them mixed up. And let's do the same thing down here. That's not inside the loop, so I'll exdent it, and F7 to see if that builds properly. So remember that this is just one pass through the array. We're not going to see that the array is sorted. We're going to see that it is more sorted than it used to be. So here are the array values before we did the sort, and the array values after we did the one pass through the array. Notice that the value 98 has bubbled up to the top, and these other ones are more sorted than they used to be, but they're still not sorted. 75 is moving to the left, 87 is moving to the left, 68 is moving to the left, 95 moved all the way to the right, well, several places to the right. So now what we have to do is repeat the action that we have here. This is a single pass through the array, and we'll do size minus 1 passes. So I'm going to put a for loop, and let's declare another variable called pass that we can use to control the outer loop. So pass gets, how many of these do we want to do? We want to do it 5 times. Let's do 1 through pass is less than or equal to size minus 1 pass plus plus. There are different ways of making a loop go 5 times, as you know, but let's see if this is comfortable for you. We'll do it in the normal way of counting, human counting. Pass starts at 1, and the last time this is true, less than or equal to size minus 1. So less than or equal to 5. The last time this is true is 5, and we will go from 1 through 5, or we'll do this 5 times. Okay, so now I'm going to put the close brace, and I'm going to fix up the indentation. So the inner loop is controlled by the outer loop. How do I do the indentation? Edit, Advanced, Format Selection. There. This is called a nesting loop. We're repeating our repetition. And I want to just run that. Let's build it and run it. See if it is sorting the array. This time when we output the array after we do the sorting, we should have all of the elements in sorted order, and then we'll walk through it in the debugger a little bit to make sure that everyone understands exactly what the algorithm is doing. So let's run this without looking in the debugger and see if all of these elements are in the right place. So it seems to be successful that we can sort an array of size elements using a bubble sort. Let's go back into this environment now, and I'm going to put a breakpoint here where we start the sort, and let's run to that breakpoint. Okay, so down here we have the local variables are available to you. We haven't started yet, so a lot of these just have junk in them. The array grades, you can pop that open and see what's in the array. This is the original values. And I will open and close that as we go through this. So let's execute one line at a time, and you can do that either by clicking on Step Over, or you can hit F10. So I'm going to go back to the way that I've always been used to doing it and just F10 through this. So we're in the first iteration of the outer loop. So pass is 1, and now we're going into the inner loop. I is 0, and now we're going to compare grades sub 0 and grades sub 0 plus 1. 95 is in grades sub 0, is greater than 75, which is in grades plus 1. Is that true or false? It's true. So when I hit F10, we're going into the if statement. Temp gets grades sub 0, so the 95 goes into the temporary variable, and then grades sub 0 gets grades sub I plus 1, so the 75 should move into grades sub 0, and it did. And now we need to put the 95 here. Luckily we stored it in a temporary variable, and we can say grades sub I plus 1 gets 95, or what's in the temporary variable. So let's execute that and make sure that yes, we did swap the 75 and 95. Okay, look at where we are now. We're at the bottom of the inner loop, and we're going to say I++. So we're still in the inner loop. We have to finish the inner loop before we start the next pass. So I is still less than size minus 1, and now we have I is 1 and I plus 1 is 2. So we're comparing the next two elements in the array, 95 and 87. Is 95 greater than 87? Yes, it is. So let's put the 95 into the temporary variable, and then we put the 87 into grades sub I, where I is now 1, and then grades sub I plus 1 will get the temporary variable. So the value 95 and 87 have been swapped. on the second iteration of the inner loop. Now let's do it again, and we'll see that the swapping was required again, and the value 95 has moved into position 3. And we're still in the inner loop. What are we comparing this time? Where I is 3, we're going to compare 95 and I plus 1 is 4, 95 and 98. 95 is greater than 98 is false, so we won't do this swapping. And now the last iteration of the outer loop, we're going to compare 98 and 88, where I is 4, grades sub 4 is 98, grades sub I plus 1 is 88, and we do have to do the swapping because these are not in the right order. And there we saw that the 98 moved into the last position. So we shouldn't let I go to 5, or we would be comparing 5 and 6, and there isn't a 6. So this condition now should be false. So 5 is less than size minus 1 is false. 5 is less than 5 is false. So we've completed one pass through the array. Now we're at the bottom of the outer loop, and we're going to increment pass. Pass is now, let's find it in the variables, pass is now 2, so we're doing the second pass through the array. And when you come to this for loop, we start at I gets 0 again. So it's as if you came to this for loop for the first time. You execute expression 1, I becomes 0, 0 is less than 5, and we're starting the second pass. So we're going to look at the 0 and the 1. 75 is greater than 87. That should be false. So we don't do the swap. I increments, and now we're going to look at 87 is greater than 68. And that's true, so we are going to do the swap. Temp becomes 87, and then move the 68, replace the 87, so we've swapped the 68 and the 87. So let's step through this a little more quickly. Sometimes we'll skip the swap, and sometimes we will execute the swap as we complete this second pass through the array. Okay, so the second pass is done. We're going to start on the third pass, and here's the execution of the third pass. So you see the inner loop happening, and then go to the outer loop and start the next pass. And when you get tired of this, you can set a breakpoint somewhere after the loop and say continue again. This is the same button as the start debugging button. So what we should see now after the bubble sort is that the elements of the array are in sorted order. Okay, it's important for you to write your own code that does this, even if you're kind of copying from what I've written. That would be a little neater. The code that comes off of your fingers is much better understood than just watching someone else do it. So writing code that has this complexity, we have a nested for loop with an if statement in the inner one. It's a good idea if you would type this and have it working on your own machine. Okay, we're going to look at another algorithm. There's a common problem as well, that we want to find something in a piece of data, so we're going to look at searching algorithms. And we'll look at two, one very simple one called a linear search, and then a more interesting one called a binary search. So assume that you have large amounts of data, and we know that efficient sorting and searching will start to become important, but we're going to look at searching data in a small array, and then you can just assume that it would be the same problem in a larger piece of data, a large database, for example. So the objective is to locate a specific piece of data in an array. And the first algorithm, a linear search, is a very simple one. We would say, let's look at the first element and see if we found it, and if we haven't, then look at the next one, and if we haven't found it, then look at the next one. It's really a very simple algorithm, a single loop where you go through an array and look for a key value, where the key value is the piece of data that you're looking for. And a binary search, which is a more interesting search, is much more efficient than a linear search. A linear search, how long would it take? Suppose we were looking for the value 75. Well, it would take only one comparison to find 75 is at position 0. Suppose we were looking for the value 99. It would take 13 comparisons to find the value we were looking for. So a linear search, on average, you find what you're looking for when you've looked at half of the data, or n divided by 2 comparisons. So there are 13 elements here. N divided by 2 is, I guess, about 6.5 comparisons on average to find what you're looking for in this array. If you had 12,000 elements, we might have a more realistic problem in terms of discussing the efficiency. So linear search simply means start at the beginning and look for the value in the array that you're seeking, and the objective is to find the location of the data that you're looking for. So a binary search is a more interesting algorithm, and we're going to write a binary search. But first of all, we'll look at how the binary search works. So here's an example piece of data. We have 13 elements in an array, and we're going to say, let's look for the number 89. Well, you can just look here and see that 89 is at position 7. So the result of this algorithm, the answer that we're looking for, is 7. That's the position of the key value that we're going to search for in this array. So first of all, look at this line. This is considered to be the search space. We don't know anything about the location of the value 89 except that it's somewhere in the array, maybe. So our search space is the whole array. The first thing we're going to do is to check in the middle of the array. So the lowest possible index is 0 and the highest possible index is 12. So the middle of that is 12 divided by 2 is 6. So let's look in the middle at array sub 6, and we find that the array sub 6 is 87. Did we find what we were looking for? The key, we were looking for 89. Well, we did not find it there in the middle. We found 87. So then we ask, is the key greater than or less than what we found? So the key is 89. It's greater than 87. So what we can do now is say our search space is now in the range of 7 through 12. We've eliminated all of this part of the array by looking in the middle and deciding that what we're looking for must be on the right-hand side. So our search space is now from 7 to 12. And we're going to do the same thing again. We're going to look in the middle of the search space. 7 plus 12 is 19, divided by 2 in integer arithmetic is 9. So the middle of the search space now is array sub 9, and it has the value 93. Did we find what we were looking for? No, we didn't. And we ask the same question. Is the key, what we're looking for, greater than or less than what we found? We're looking for 89, and that's less than 93. So our search space is now this small part of the array, 7 and 8. This is called a binary search, binary meaning 2. we're going to cut the search space in half each time we look in the middle and decide whether to go on the left or on the right. We don't need to look at 9 through 12 anymore. We already looked at 9 and we found that it wasn't there, and we know that it's not in elements 10 through 12, so the search space is now 7 through 8. So we're going to do the same thing again. Check in the middle. We don't really have a middle of two elements, but we'll do the same calculation. 7 plus 8 is 15 divided by 2 is 7 in integer arithmetic, and that means that we're going to look at element 7, and we found what we were looking for, and so the algorithm is over. This is very efficient. It took us only 3 guesses. Where did we look? We looked at element 6 and we didn't find it there. Then we looked at element 9 and we didn't find it there. We looked at element 7 and we didn't find it there. You might notice that if we had been looking for 90 instead of 89, it would have taken us one more try. We would have had to guess 4 times instead of 3. So think about how many guesses or how many comparisons do we have to do before we're guaranteed that we will find the answer. And it turns out that there is a way of measuring this. For a binary search, we're guaranteed to find the key where 2 to the power of guesses is greater than n. N is the size of the array. G is the number of guesses it takes, or the number of comparisons it takes to find the value that we're looking for. It took us 3 guesses this time. 2 to the power of 3 is 8. 8 is not greater than 12, so we were a little bit lucky to find 89 in 3 guesses. 2 to the power of 4 is 16. 16 is greater than 13. N is 13. We have 13 elements there. We would be guaranteed to find what we were looking for in 4 guesses or fewer using a binary search. Remember the linear search algorithm that we looked at before. In a linear search, we would start at the beginning and look for, oh, there we found it. It would have taken 8 comparisons to find the value 89. When using a binary search, it took us only 3. On average, the linear search takes n divided by 2, 13 divided by 2, probably 7 guesses, and using a binary search, 4 guesses. Well, the difference between 4 comparisons and 7 comparisons is not very much. You have to imagine that these arrays of data that we're searching in are very, very large, and that's when this exponent starts to become very powerful. For example, if I had 2 billion elements in the array, how many comparisons would it take to find a number using a linear search? Well, on average it would take n minus 2 or 1 billion guesses, and using a binary search, 2 to the power of g is greater than n. I think it's 31 guesses or a billion guesses. Now the difference between a linear search and a binary search becoming very significant, even on fast computers. Let's look at the pseudocode for a binary search algorithm. And this is written as a function where we're going to pass in an array of data, the size of the array, and the key. The key is the value that we're looking for. And we have 3 variables: the low index in the array, the high index in the array, and the middle index in the array. And to start the algorithm off, the search space is all of the elements of the array. So the lowest value that we'll look in is 0, the highest is the last element of the array or index size -1, and middle is where we're going to look. So we're going to implement this as a while loop, and this loop will keep going for as long as there is a search space. When the search space closes up to have no elements in it at all, meaning that the low passes the high, then we can conclude that what we were looking for is not in the array. So, calculate the middle, determine if the key was found. If it was, then we can bail out of the algorithm early, return with the information that we were looking for. If the value that we found in the middle is greater than the key, then bring the high index down to the middle. Otherwise, bring the low index out to the middle. So this is the part of the algorithm that cuts the search space in half. Depending on what we found in the array, we're going to move the high or the low into the middle, the current middle. And if we don't ever return with the location where we found the key value, if we don't ever return from there, then we can conclude that we did not find what we were looking for in the array, and we will return -1. So -1 is not a valid index into an array, and whoever calls this algorithm will recognize that if it returns -1, then the search failed to find what it was looking for. Okay, this one is a little bit complicated, as was the bubble sort, and we're going to go into the development environment and develop the solution to this together. We'll implement this one as a function that accepts an array and returns the location where it found the key value that was being searched for. Okay, we're in the development environment again, and we're going to work on the binary search algorithm. So now's the time for you to pause the video and get your C project up to this point. So I entered the same numbers that we had on the slides, and we're going to write a function that will do a binary search, returning the position of a number that we're looking for. So I'm going to flip back and forth between the pseudocode solution to this function and the code as we're writing. So we'll write this code from the pseudocode solution. Before I do that, I'm going to declare the variable key and just say that what we're going to look for is the number 87. So that will be the key value that we'll search for. So I'm going to put the binary search function up here. It's going to return an int, which is the location of the key. And let's call it binary search. And it's going to take an integer array, the size of the array, and the key value that we're looking for. So there's the function signature, and the function call, the result, declare a place to hold the result, and let's say result gets binary search, and we will pass in the array. We'll pass in the size of the array, which is a defined constant with 13 in it, and the key that we're looking for. So in this case we're looking for the value 87, and this result variable will have in it what the function returns. So the function might return -1 if it doesn't find what it's looking for, or it might return the index or the position in the array where it found the key value. So 0, 1, 2, 3, 4, 5, 6. I wonder if I got this wrong. I'm going to have to go back to the slides and make sure that this corresponds to the numbers that we were using. So 75, 77, 80, 80, 82. We wanted to find 89 at position 7 to match the slides. So we're going to look for the number 89, and we expect to find that at position 7. Okay, I want to have the code always compiling. So we have a binary search function now that doesn't really do anything. It returns -1 all the time, but that's okay. So long as it compiles, we can use the debugger to make sure that our logic is correct. So after we get the result, let's print it out. Let's just say that %i was found at location %i. Okay, so we're looking for the key, and we're going to output that where it was found. So let's see if that's working. I don't want the implementation of the binary search to be complicated by these other things. So we're saying 89 was found at location -1. Okay. So we did call the function, we did pass in the information, and we returned -1. So now what we have to do is to implement the binary search algorithm here. And let's flip back now to the slides. So here's the binary search function. We need to keep track of the search space in terms of the lowest possible value in the search space and the highest, and this variable, which we'll calculate each time, will be the middle of the search space, where we'll look for to see if we found the key in the middle. So let's declare those variables inside the function. These are local variables to the function. So low always will start at 0, and high will always start at the size of the array -1, and we need a variable called middle that we will calculate inside the loop. So we have a while loop, and this while loop will continue while low is less than or equal to high. So as long as there's still something to check, we will keep going. And the first thing that we need to do inside the loop is calculate the middle of the search space, and the middle will be the low plus the high divided by 2. And all of these are int variables, so that will be an integer value result. Even though it's a divide by 2, we don't want to use as an index like 6.5 or something like that. That's not a valid index into the array. So we look in the middle and we say if the key, which is the value we're looking for, is equal to the array submiddle, then we found what we're looking for. So we can immediately exit from this function. And what value do we want to take back to the caller? What will we return? Well, we don't need to return the key because that was passed in. We don't want to return the whole array. We don't want to return array submiddle. We want to return middle because that's the location where we claim to have found, well, we have found the key value. Okay, so if that isn't true, meaning we didn't find what we were looking for, then we want to see if the key we found, if the value in the middle is greater than the key. If the value in the middle, that's array submiddle, if that's greater than the key, then what do we want to do? We want to change the search space. If the value in the middle is greater than the key, then we want to change the high index of the search space to middle -1. And there is only one more possibility. We either found it, or the value we looked at is greater than the key, or the value that we looked at is less than the key. So we don't even need another condition. We can just say low gets middle +1. These +1s and -1s might not be obvious to you. It just means that we don't need to look at the one that we just looked at. So we don't need the search space to include the middle value because we've already looked at that value. And so we would subtract 1 as we move the high end of the search space into the middle, or add 1 as we move the low end of the search space into the middle. Well, it's fairly complicated and not very many lines of code. I'm going to compile this to see if I've made any mistakes. And we will walk through it in the debugger and see it work. So the build succeeded. Let's set a breakpoint here and go back and look at the main function to make sure we have an array that we're going to pass in. The array in the main is called grades. That name does not have to match the name of the parameter in the function. So up here we just called it array because I wasn't very creative. You can call that anything you want. It doesn't have to match this is a local variable to the function. And size, we're passing in the size of the array, and we're passing in the value in the array that we're looking for. If we find it, we'll return the index in the array where we found the key. If we don't find it, we will return -1. Okay, let's run this program up to the breakpoint, and we will look in the debugger and see if things are going the way we expect. So the size of the array is 13, the key, the value we're looking for is 89, and our search space between low and high is 0 to 12, which is all of the elements of the array. And oh, this is kind of interesting. We cannot pop open the values of the array in the debugger here. You don't know exactly why yet. You'll learn that when we talk about pointers in the upcoming segments. But we're going to look at the values in the array. We're going to have to go back down here and just use this as a reference. Okay, so let's start walking through this and get a feel for what its behavior is. Low and high are 0 and 12, so 0 is certainly less than 12. And let's step in. Low plus high, 0 plus 12 divided by 2. Middle should become 6, and you see that it does. Now we're going to look to see if key 89 is in the middle of the array. And it isn't. What is in array submiddle? Array submiddle has 87. I'd like to show you something else that's kind of interesting. If you want to watch something like array submiddle, you can just paste that into a watch window. And array submiddle has 87 in it. It will calculate this as you go along. So if we want to watch what's in array submiddle, you can add that into a watch window, and you can watch as many things as you want. It's really a convenient thing to have. So we're going to look at the locals, and we're going to look at the watch window. So we have the key value of 89 and the array submiddle is 87. Those are not equal. Array submiddle 87 is greater than the key, true or false? Well, that's false. So as we step through this, when we check that condition, we'll go to the else part, and now we'll say low gets middle plus 1. So we're moving the low end of the search space into the middle of the array, cutting the search space in half. So now our search space is from 7 to 12. So the next iteration through the loop, 7 is less than or equal to 12. That's true. Calculate the middle again. The middle now is position 9. And did we find what we want? What is in position 9? Array submiddle has 93. So we have not found what we're looking for, but 93 is greater than 89. So we're going to change the search space this time by making the high middle minus 1. And middle minus 1 is 8. So now our search space is starting to get very small. Positions 7 and 8 are the low and high. And the next iteration of the loop, we have positions 7 and 8 is the search space. Calculate the middle. The middle of 7 and 8 in integer arithmetic is position 7. And the key, what we're looking for, 89, is at position 7. So we found what we're looking for, and we're going to execute the return statement. The return statement, you'll remember from the section on functions, takes us out of this function immediately. So if I just execute that return statement, we will, okay, it's showing that it's leaving the function. And now we're back at where the function was called, and the result variable in the main function has 7, which is the value that was returned by the binary search function. And we should output that 89 was found at location 7. Okay, so that seems to have worked for when we're looking for something that was found in the array. Why don't we try changing the key, the value that we're looking for, to something that isn't there. Let's try 91. So we're going to walk through this algorithm again, looking for something that isn't there, just to make sure that it doesn't blow up or give us back an answer that's wrong. And we will run to the breakpoint again, which will take us into the function. This time the key is 91, and we're going to step into this loop. The middle is 6 as usual. We did not find 91 at position 6. Array submiddle is 87. 87 is greater than the key is false, so we'll bring the low. This is going exactly the same as it did the last time. Our search space is now 7 through 12. Calculate the middle again. We're going to look at position 9. We didn't find it at position 9, but we're going to bring the high end of the search space in. So now the search space is 7 and 8. Calculate the middle of 7 and 8, and in integer arithmetic it's 7. So what do we have this time? 89 is greater than 91. That's false. So we're going to bring the bottom of the search space up to 8. Now the search space is one element from 8 to 8. that's still valid. We might find it in a search space of one element, and the loop continues because it's less than or equal to. So we've got a search space of one element. The middle of 8 and 8, you might guess, is 8. And now, did we find it at position 8? We did not. So with a search space of only one element, we didn't find what we were looking for. And we will again change the search space. So the low index will become middle plus 1, which is now 9. So our search space is a low of 9 and a high of 8. That kind of means that our search space has collapsed into nothing, and there is no place left to look, and this loop will end because low less than or equal to high is no longer true, and we can conclude that we did not find the value 91 in the array, and we'll go back to the caller with result. So this function call evaluates to -1, which is what was returned. Okay. These algorithms, not very much code, and just a little bit tricky. You wouldn't be expected to, at this point, develop your own algorithms of this complexity, but you are expected to be able to analyze them. So walking through this and demonstrating that you can understand exactly what this algorithm is doing is key at this point, and it will develop your skills of manipulating arrays and walking through algorithms that have multiple variables and seeing how multiple variables interact. So just a short summary now of the things that we've looked at in this segment. There are many well-known algorithms that solve common problems, and we looked at two of them, the bubble sort and the binary search. We also briefly looked at the linear search, which is a very simple one-loop search algorithm. We wrote a bubble sort that included nested loops, and we wrote pseudocode that helped us to have an understanding of the algorithm. You can use pseudocode as an intermediate step between understanding the problem and writing the code. Some people like to do this and some people don't. Some people just work directly with writing the code. Sometimes if you write the code with a pencil or a sketch of the code, then that makes actually typing in the code solution faster. You come closer to the right solution from the beginning. And it takes a great deal of practice to get used to using nested loops and using arrays, and we've used these algorithms for two purposes. One is to get you comfortable with walking through loops that use arrays, and the other one is to introduce some common existing algorithms. There are many algorithms existing for doing things like sorting and searching. The bubble sort is only one of the algorithms that's well known for sorting. You can use other sort algorithms such as the selection sort, insertion sort, quick sort, and so on. This sorting, the job of writing an efficient sorting algorithm, is pretty much solved. People would, instead of writing a sorting algorithm, they would look for a sorting algorithm that exists that would meet their needs. The binary search that we looked at is a much more efficient search algorithm than linear search, and you might have noticed that the data must be sorted before a binary search will work properly. So when you cut the search space in half, you have to know that what you're looking for is in the half that remains, and that implies that the data had been sorted. So there's a relationship between the sorting and searching algorithms that we've looked at. So I encourage you to walk through the code, keeping track of the variables as they change with pencil until you're very comfortable with the binary search algorithm and the bubble sort algorithms. This is an important place in your understanding of how these algorithms are working. Well, I hope you've enjoyed working with searching and sorting algorithms, and I'll see you in the next segment.